There we go. Now I got it turned on. I love the lights. It makes it almost impossible to notice the room's half empty. So yeah, thank you, Mats, for the introduction. Computational storage is something that has definitely been near and dear to my heart. Sat down in a room in 2018 with a few other colleagues and kind of coined the phrase for the marketplace, even though it's been around a lot longer than that. So what we're doing here is this is a collaborative effort that took place across multiple companies. As we go through the presentation, I'll give credit where credit is due. But to the point Tim was making about trying to find the killer app and how to make a block storage device that has data sharded across multiple locations, how do we make things work? And so basically what I'm going to try to do is walk through some material that was put together by Mike Meunier from Intel Labs and a colleague of mine at Solidigm, Hermes Alexandra Alcantara Silva Costa, my good Brazilian buddy. So these two guys did a lot of the actual technical work. I'm here just to present the cool work that they did. So if I speak ill of it or don't have the right answers, it's because they're not in the room. But basically, when we're looking at this, we're trying to figure out how to take, very similar to what Tim said about an application and make a block storage device aware of what the application is, or how to properly deal with things like rated data, sharded data, data in different places, because you have application layers that are doing all kinds of things to speed the systems up because the storage is so slow and it's in block form and it has all this stuff, and we're still dealing with the legacy of the hard drive infrastructure and still have hard drive infrastructures in a lot of the OCP frameworks. So how can we do something a little different and look at it in a new kind of way and an innovative technique of that crawl, walk, and run scenarios that exist for the computational storage marketplace. So what we're trying to do here is we're going to go through the process of teaching the devices about the data and how to do that. And it involves some today proprietary type work that we've done in the wings of what's being done in some of the other standards bodies. So OCP is one of the groups that's doing things with this OCTI. There's SNIA that's doing work in the Computational Storage Working Group. There's NVMe that's doing work to create the command sets. In the process of doing all that, we still got to show things that work ahead of that, if you will. And so that's what we're trying to do here. And you can see that in this particular case, we're talking about even coming up with the idea of a new command on how to do search and looking for certain different things in locations and sharded data. And this was a paper that was printed all the way back in 2019 by Mike and his friends. So why we're doing this is it helps us bridge into the next generation of architectural options. So you have, of course, the big buzzword of today. If you don't mention the word AI or the letters AI in your presentation, you shouldn't be at this event. So we have AI applications for you. You know, take your pick: machine learning, deep learning, large language models, whatever you want to call it. But yeah, there is great opportunity for this technology, and what we're starting with here to branch out into even more of what you can do with these architectures. So sorting, searching, filtering, low-level storage services. One thing that is key to point out about the concepts of dealing with computational storage is it's not about replacing architectures. It's not about doing something because I want to do it here, not there. It's how we look at the ecosystem to make it all work together better. So there's a lot of times I've been in conversations with people, they're like, well, what about this? And it's like, that's great, it has its application. So for example, Tim's FCM and his custom and proprietary environment, great opportunity to make compression work. The average Joe can't do that. They don't know what their user is going to do with the compression algorithm, so they can't guarantee a 2-to-1. So if you have a system like his, he's got a great solution for you. It's a computational storage move forward, but we've got all these players that are doing different things. So how do we get to the end goal? And you look at like the petabyte SSD platform, and they've got the DPU, and they need that. It's a necessary evil of the entire environment. It's not about where do I do compute, it's about which elements need the compute and where. And that's what we're working on with this stuff. So what we're doing is, in this case, it's called data scrubbing, is the term we've decided to use for it. And what we're trying to do is take away the low-level tasks that the CPU's been doing that we all know it does, but didn't realize it could be done better. So I'm not trying to speed the system up by nature of doing analysis of data. I'm actually doing speeding of the system up by looking at what's making sure the data is accurate. So looking at the metadata, managing with the metadata. That way I don't care if the data is intact on the drive. If it's sharded across 16 drives, that's just great. Each shard still has to be verified and validated, and that's something that I can do at the drive level and not have to push from the host all the way through the system and actually cause interrupts and things like that. So it looks at something that's not necessarily compute intensive. It is read intensive, so it can get in the way of the system if you're doing it in an efficient manner. And it tends to not be scalable if you have one or two socket system that's trying to look at all the drives in the box. So if I've got 32 drives in a nice one of the OCP platforms with an E1S, you can't really do that efficiently without doing some kind of scalable improvement in the system. And so what we did in this particular one to showcase how it works is, to the comment that was made earlier about TCP, great, we like TCP IP. We took one server that is our compute server, we took one server that's a storage server, and we offloaded to the drives themselves the different features of the computational storage that we can do for purposes of data integrity. So the reading, the scrubbing, the dedupe, the search, and even the intrusion detection to some extent. So we're not even just doing one application, we're doing a whole bunch of small, low-level, high-impact solution value add. Pick your favorite acronyms. I'm trying to go way too fast here. But we're helping the systems let the CPU do other work that really needs to be done on the actual user data. And so if you look at it from the perspective of the results that we saw, you can see that it was an Ethernet bottleneck. At 10 gig, 40 gig, 100 gig, you can get line rate performance. But if you're not doing that and you throw in the computational storage, I'm no longer moving everything off through the network from the storage server to the compute server to look at the data and push it back. I get a significant increase in performance in the system. And as you can tell, I can even do it faster to some extent, depending on the number of drives, with the drive level analysis versus the CPU level analysis. So if I remove the networking bottleneck, because there's always a bottleneck, the next bottleneck is the CPU. So then beyond the CPU, what's left? The storage device itself. And if I've got a whole bunch of storage devices, my aggregate performance can actually show better overall throughput for the system, because all that work that's being done by the drive is freeing up the host to go do other things. So what we did with this is we put together an actual demo. We demoed it at the Flash Memory Summit 2 months ago here in San Jose. These are the 4 companies that have been working together on this particular project. So we've got MinIO from the database perspective. We've got to have sharded data to work on. Intel helped us with a computational storage library. VMware is helping us with the hypervisor for the virtualized environment perspectives, and then we provided the storage devices. And so before, I can't pull a Tim, I can't go out in the hallway and offer you the Cache app. This is a prototype. It is not something that is POR today. If you're interested, definitely let me know. It helps me get it POR because I can show interest in it. But this is one of those examples of where our R&D and our pathfinding teams come together and say, let's do something unique and show the world something new. So we chose to do this because it does offload the host. It reduces the traffic across the network, as we've already shown. It reduces the host memory footprint, believe it or not. It frees up the memory footprint because I'm not storing all that data in memory while the CPU is acting on it. I'm doing it all in the drive. So I can either use that memory for other aspects, or I can actually reduce the size of the system. So there's multiple ways you can take advantage of this. And then it's scalable with the storage itself. The performance improves by the number of drives you have. So what we have here is the way that we're doing this particular solution set is we have on the one side we have the application layer, the MinIO platform, the file system. We've got an NVMe TCP IP link that talks to the device drivers, and then we have the NVMe link that talks to the drive on the other side. And you can see there's our built-in hardware engines. So these aren't even software driven, these are hardware driven engines. And we're taking a file, we're sending it over to the drive along with its LBA list and with the vendor unique command, and we're putting the data in, and then we're going to read it back in the buffer. We're going to do a data integrity check on that data in the drive itself. We're going to confirm that information, and then we're going to let the host know that, by the way, you've not only written data, but we can guarantee it's the right data, and none of that verification took place within the host system. It all took place within the drive level. So we've been able to augment every write to the system by way of doing this data integrity verification in a hardware engine on the drive itself. So this is kind of what I would classify as almost a bare metal implementation of computational storage, because I'm not requiring a high level of software input. It's still a host-driven activity because we're using NVMe and TCP IP packets to tell the drive what to do, but the drive can accomplish those tasks on each and every read and write of data. And then, of course, we can free up the internal buffer because, like Tim said, all drives have to be a drive before they are a compute drive. So all the read and write of the device are always prominent and important aspects of it. All the data integrity checks and things are done in the background. So if you look at it from a scaling perspective, you can see the host, once you hit a certain level of a Xeon performance, it can't get any faster doing this particular task because you've got one CPU that has so many cores associated to it that are offering this particular offload. And then, but as we put in the individual drives, since we can count each drive as completing the task simultaneously, these are all working in series and parallel with one another, we're able to see it scale in the overall performance of the system when it comes to completing this particular task. Because the more drives I have, the more individual operations that are occurring in a concurrent fashion. So we've got a prototype. We've had some fun. We've got some big name companies that are working together. How do we get it from where it is today to something that you can buy and can put in your particular server? So one of the first things that we're trying to do is make sure that we're aligned with the industry standardization efforts around computational storage and NVMe. This allows it to become multi-source friendly, which is always a thing for everybody in the marketplace today. So at TP 4091 is in the process of being ratified. And once that's done, we can convert our vendor unique information into these traditional NVMe commands. The SNIA Computational Storage Working Group has put together an API to help issue the commands back and forth and allow the host to have the ultimate control of which aspects of it are offloaded. So we're working together in that effort to align to the API that was recently released and even won an award at Flash Memory Summit for its cool new work. And then, of course, we have to continue working here on aspects of how it plays and parlays in. One of the unique things about all these standards bodies is we have SNIA, we have NVMe, we have OCP, we have all the other acronyms you can think of that have to work together. And part of the fun of this is making sure that we work in a cohesive method and manner so that when one group does an effort, it doesn't break another group's work. And so OCP has kind of been on the wings of looking at computational storage. This is probably one of the first years I've been at the event where we've actually had dedicated time to it. So it's great to see that there's some new traction here and looking forward to what we can continue to do there. So once we've done that, that's the kind of the crawl, and now we need to get to the walk and run. So a future opportunity also is this concept of dynamic resource allocation, where we can actually have the ability to not only do simple bare metal like data integrity checks or other hash type work, CRCs, but we can actually add a level of compute, and that can be represented by multiple different frameworks. One example would be put a Linux kernel inside the device. One could be running ESXi inside the drive to help with the VMware side of orchestration. But all of this allows us to say, hey, let's take an opportunity to expand the horizons of what you can do with a computational storage drive and take advantage of those compute resources that can either be added in the way of an additional engine like an ARM core or RISC-V core to an SSD, or in an offload in some way like a chiplet down the road as we look at all the advancements that are taking place there and kind of future generations of products, or even allow us to have the compute be more prominent than the stored, the SSD activities. So you can actually mitigate and manage all of that with this kind of dynamic resource allocation and a true high-performance compute engine built into the device. So at the end of the day, computational storage is ideal for these low-level tasks on device. And I just want to call that out and make sure that, as we talk about this concept of playing well in the ecosystem, if you've put data in a drive, the gravity of removing it from the drive to do work on it is always going to be more complex than just working on it in the drive. Now, the analogy I use for this when it comes to the overall marketplace is take a look at your traditional autonomous car. Anything in the driver's seat forward, I'm going to use your GPU, your CPU, your DPU. It's all going to be memory driven. It's real time. I have to have it now. But anything that's behind the driver, map updates, traffic monitoring, routing, all that kind of stuff that can take a little bit longer to do and is done on data that is stored in a device, not in a memory, is a computational storage solution path. So I just want to kind of put that thought in everybody's mind as you're thinking through how does computational storage play into with CXL and GPUs and DPUs. Where your data is located and the amount of effort you need to put to get that result out are the key aspects of how this works. So you have computational memory because I'm playing in memory, I need it real time. You have computational storage for anything that's stored on a drive, and you're trying to offload the gravity of pulling data out of that drive. And as we get into 60 terabyte drives and 100 terabyte drives, anything over 8 terabytes really has been proven to show it takes more work to get it out of the drive than to just push some kind of compute down to the drive and let it take a little longer. So it's not necessarily about getting it done now, but it's about getting it done efficiently and in the right place in a sustainable fashion too, from that perspective. So overall, that's kind of the concepts of what we're doing here with the data integrity is we're offloading some simple functions that is not looking at the actual user data, it's looking at the metadata alongside it. So I don't care what form it's in, what sharding it's done, what RAID level you've got into it. And as we get to the next levels, we can start playing with more actual compute on that data as these ecosystems change and evolve. So with that, I will, it looks like I have one question.
Can't let late afternoon be boring.
No.
So really interesting. Have you thought about it? Let's see, so it looks like everything you're doing right now, the host issues a command, the drive does the integrity check. Is that correct? Okay. Have you thought about adding what this, which is effectively higher level scrubbing, to the background scrubbing that the SSD is already doing?
It does absolutely play into the capability of doing that. Again, to the point with that one is the scrubbing is the easy part. I can verify the 0 and 1, but I need to know what the host wants that result to look like. So there's an aspect of still teaching the drive what that response would be as part of the data scrubbing to the host.
Understood. And the host might appreciate being told that things have gone bad when they've gone bad, as opposed to being told 3 weeks from now when it goes and takes a look.
Yeah. And to that point, that's a really good example when you look at data scrubbing and future of computational storage. How about a machine learning algorithm that takes a look at what the data scrubbing is doing and trains itself to know that the data is starting to wear out in a certain block, and you can pre-predict that block failures instead of having to do reactive block failure recovery in the drive. So that really adds a next level of the ability to ensure that these large capacity drives do not have downtime when you end up with a bad block or a bad page.
Do we have any other questions? Well, I have one there. So for this, what you presented, is this pretty much going to be fully supported with TP4091?
Yeah, it was actually written with the concepts of TP4091 in mind. It started as vendor-specific, very unique TCP/IP stuff, but we're able to actually migrate it fairly comfortably with the current state of TP4091.
And do you know when TP4091 may be?
Actually, I don't. I do not know the current state of that one. So.
Okay, let's thank our speaker. And
Thank
this
you.
is the end of this session. And I think please stay for the panel that's coming up afterwards.